Welcome to Physics Clinic at the Red Rose Academy. This one equation changed electrochemistry forever. In 1889, Nernst discovered how concentration affects cell potential. His equation is E is equal to E electrode minus 0.0591 divided by N into log Q. So this is the equation we are going to learn about all these things, okay? What is the Q factor and everything, okay? This equation predicts battery voltage, electroplating, corrosion, fuel cells, and even biological cells. Okay, that is why every NEET and JEE students must master it, especially for board exams also. So today, we are going to learn about one of the most equations in electrochemistry, the Nernst equation. If you ever wondered why battery voltage changes over time or how scientists predict the voltage of electrochemical cells, this lesson will make it crystal clear. Okay, so now let me explain the standard electrode potential, which is measured under certain standard conditions. Okay, so you must know that. Let me show you. In the last class, we learned about electrode potential, right? For a galvanic cell, we learn what is electrode potential. Electrode potential is the potential difference, right? Developed between the electrode and the electrolyte. Okay, when the concentration of all the species involved is unity, it is known as standard electrode potential. Okay, then we saw cell potential also. Cell potential is the difference between the electrode potentials, okay, of the cathode and the anode. That also you know. Okay, then EMF of the cell, everything we have studied. From here, we have learned about EMF of the cell. What is the EMF of the cell? E cell is equal to E right minus E left, right? So everything we have learned, okay? In a galvanic cell, the anode has negative potential, okay, with respect to the solution. And cathode has positive potential, okay? And cathode has positive potential. And in cathode, it has positive potential with respect to solution, okay? Then, so you must know the standard hydrogen electrode potential. Standard hydrogen electrode. Okay. So what is the standard hydrogen electrode? Okay. So let me write the equation to you. This is standard hydrogen electrode. Okay. Let me explain you all these process right now. Okay. How you can measure the potential, electrode potential. So this is very important topic. You must know. Okay. So you have to measure the electrode potential. Seriya? Okay. Now, you know what is that electromotive force? Okay, everything I discussed about in the last video. Okay, so for example, we can write the cell reaction as copper solid plus 2 Ag plus aqueous, Cu2 plus aqueous, and 2 Ag solid. So you know all these things. In the last class itself, I taught you fully about all these things. Okay. So yes. Okay. So, how you can understand what is anode, what is cathode, and what is oxidation, what is reduction, and everything. Okay. Now, you know about how to write the electrode reaction also. Everything I taught you in the last video. Now we can see now half cell called standard hydrogen electrode. Okay. So what is that half cell? So the potential of individual half cell cannot be measured. So we can measure only the difference between the two half cell potentials that gives the EMF of the cell. That's what E right minus E left, right? So if we arbitrarily choose the potential of one electrode, that is half cell, either anode or cathode, then that of the other can be determined with respect to this. Okay, wow? So that means with this you can able to find out with this relation. Okay. Then, if we arbitrarily choose the potential, for example, we can choose any potential, any either anode or cathode. That's what arbitrarily choose any one of the potential, then the other can be determined with respect to this. According to convention, half cell called standard hydrogen electrode, represented by platinum solid, hydrogen gas, H plus aqueous. It is assigned as a zero potential at all temperatures corresponding to the equation. You know this vertical sign and double vertical sign and everything, in you just refer last video also, so it's very important for you. Okay, then the standard, this is hydrogen electrode, H plus aqueous plus E minus. Okay, so what is this H plus aqueous? Okay, that means hydrogen lose one electron, and then now it becomes half H2 gas. Okay, if hydrogen is always diatomic, Okay, if you are writing hydrogen gas, it is half of the hydrogen gas. Hydrogen plus is half of the hydrogen gas. Okay. That means removal of electron is happening here. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. Okay, so the hydrogen electrode is not given like since hydrogen is a gas, how it can be coated on the electrode. So this can be done with the help of platinum electrode coated with platinum black. So this is platinum coated on platinum foil. Okay, this one. And then downward displacement of hydrogen gases allowed to enter into it. All the gases are downward displacement. So the electrode is dipped in an acidic solution also. Okay. And the pure hydrogen gases bubble through it like this. Okay. The concentration of both the reduced and oxidized forms of hydrogen is maintained at unity. That means we are taking, this is also known as She. Okay. Standard hydrogen electrode, She electrode. Okay. So here, the concentration of both the reduced and oxidized form of hydrogen. Okay. Hydrogen can be reduced and oxidized. Okay, so both are happen and it is equivalent to unity. For example, this implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. Okay, so what is the pressure? 1 baric pressure, and concentration we are taking 1 molar. That means we have to take everything in unity. So that's what the condition is. Okay, these are all the steps for measuring the electrode potential. Okay, so that we have considered a standard electrode potential, that is the hydrogen electrode. Hydrogen electrode can be made by constructing what? Platinum electrode coated with platinum black. So this thing, and then here the hydrogen gas is allowed to pass through. Okay, like a downward displacement. Then and then it is placed in acidic solution. That is an electrolyte at 298 Kelvin. What will happen? 298 means 25 degrees Celsius. The EMF of the cell, standard hydrogen electrode. So standard hydrogen electrode second half cell constructed by taking standard hydrogen electron as anode. That is, we are taking one half cell as anode, another half cell as cathode. You are taking here this two vertical straight line. So this represents the salt bridge. There is an acidic solution also present. Okay. Then it gives the reduction potential of the other half. So how we can able to find out by means of this equation? E standard is equal to E right minus E left. Then you can find out E left for standard hydrogen electrode is 0. So how it is equal to 0? So if the concentration of the oxidized and the reduced forms of the species in the right hand cell are unity, then the cell potential is equal to standard electrode potential of the given half cell. That means you can make the left side as 0. That means what it says, what is in the left side? So you are taking here one half as reference electrode. Okay, the other half is cathode, which gives the reduction potential of the other half cell. Okay, if the concentration of the oxidized and the reduced forms. Okay, so both the concentrations, okay, in the right hand cell are unity we are taking. Okay, so in the right hand cell only we are taking as the reference cell. Left hand cell, we are making that electrode potential as 0. So everything comes to the right hand side only. Okay, we are taking right hand side as the reference. Okay, then if you make it as 0, then it will be only right hand. The measured EMF of the cell. You know, platinum solid, hydrogen gas, which is under 1 baric pressure, it becomes hydrogen aqueous by releasing one electron that is attracted by actually the copper 2 plus ion. Now it becomes copper solid. Okay. So this is how in between there is a salt bridge. This is how the reaction takes place, cell reaction takes place. So 0.34 volt, and it is also the measured EMF of this particular cell is 0.34 volt. And it is also the value for the standard electrode potential of the half cell corresponding to this reaction. See here. Okay. So similarly, the measured EMF of the cell is 0.76 voltage. Then the corresponding to the standard electron potential of the half cell reaction is zinc. So zinc is double, okay, when compared to copper. But it is negative also. 0.34 is positive and negative 0.76 has happened. Then the positive value of the standard electrode potential in the first case indicates that copper 2 plus ion gets reduced more easily than H plus ions. This is also a very important point. Okay. The positive value, why the positive value talks about, we have studied now, right? A positive potential at the cathode. So this positive value of the standard electrode potential in the first case, okay, it indicates that is copper 2 plus ions gets reduced more easily than H plus ions. The reverse process cannot occur. That is, the hydrogen ions cannot oxidize copper. Okay. So, or alternatively, we can say that the hydrogen gas can reduce copper ion. Like that, we can say, under the standard conditions described above. So, thus, copper does not dissolve in HCl. In nitric acid, it is oxidized by nitrate ion and not by hydrogen ion. Very important. In nitric acid, so this it is oxidized by nitrate ion only and not by hydrogen ion. This is very important. Okay. Then, so, and also copper does not dissolve in HCl. These are all the standard acids we saw. So, and then this is the hidden reasons behind this. Okay. And, when compared to hydrogen, copper is more, see, oxidized in nature. One second. Okay. So copper ions get reduced more easily than H plus ions we saw. So the reverse is not possible. That means hydrogen ions cannot oxidize copper. Okay. Now, This is the reason for this HCl and HNO3. The negative value of the standard electrode potential in the second case, that is zinc, we saw, right? It indicates that hydrogen ions can oxidize zinc. Zinc can reduce hydrogen ions. So this is the case. You can see this negative potential. Okay, it shows up. Okay, the hydrogen ions can oxidize zinc, and zinc can reduce hydrogen ions. Both vice versa also true. So that is the beauty of the positive potential and the negative potential. You must understand this. Okay, so half cell reaction of the particular Daniel cell is given. So this is the half cell. You know, zinc solid, it becomes zinc aqueous plus 2 electrons reduced. Okay, so then copper 2 plus, it accepts 2 electron, then it becomes copper solid. So right electrode and left electrode we can take. Always this overall reaction is the sum of the above two reactions. If you add these two, you'll be getting this reaction. Zinc solid plus copper 2 plus left side, reactant side, it gives zinc 2 plus copper solid, because this 2 electron is accepted by this copper 2 plus, so it becomes copper solid. So what is the EMF of the cell? You know, E right will be 0.34, right? That's what we saw. Copper electrode for E right electrode is copper. So it has the electrode potential 0.34. It was determined. Okay, I'll explain you how to determine, how to calculate this. Okay, we'll see it in further cases. And 0.76 negative, it is for left side. So minus of minus, you'll be achieving 1.1 electron volt. Got it? So what is this 1.1 electron volt? This is the standard electrode potential. So it's very, very important. And also, sometimes the metals like platinum or gold are used as inert electrodes. Okay, this platinum which is used for a hydrogen electrode, it is inert. It won't react. Okay, because for the hydrogen gas, it can't be like it can't be act as a solid, right? So it is now deposited on the platinum electrode, which is coated with platinum black. Okay, and then by downward displacement method, and then it is placed in totally an acid. So this is the setup we saw already, She electrode. Okay, so sometimes, okay, so they do not participate in the reaction. Okay, for example, platinum is used in the half cell reaction. We saw in the hydrogen electrode. The same thing, it is again and again repeated. Okay, for bromine electrode, you have to write like this. For bromine also, bromine is a gas. Okay, for bromine also, it is given like this. Platinum solid, bromine 2, aqueous, it gives bromine minus aqueous. With half cell reaction, you can write this. Okay, so these are all the examples given to you. So many examples you have to write, you have to practice the half cell reactions. Okay, half cell reactions means right electrode, left electrode, and we can say the half cell, anode, cathode. At anode what is happening, at cathode what is happening, and then combined reaction also you must know. So you students, you can practice for more reactions. Okay, then the standard electrode potential are very important, and we can extract a lot of useful information from them. Okay, the values of standard electrode potential for some selected half cell reactions and it is given in the table. This table is very important for you. Actually, this one. So the standard electrode potential for some half cell reaction. This is what I told you, my dear students. You have to practice all these equations. You'll be asked any of the equations from this. Okay, how it becomes. Okay, so in the form of oxidation, in the form of reduction. So both you have to learn. Okay, and then you can just calculate the ranges of electrode potential, which is having higher electrode potential, which is having lower electrode potential, which is positive, negative, everything. You can have an observation. Okay. Then, a negative electrode potential means the redox couple is a stronger reducing agent than the hydrogen couple. So that means what it says, that's what we saw already again and again, the same one. Negative electrode potential means the redox couple. Okay, the redox couple means the total reaction. It is a stronger reducing agent. Okay, stronger reducing agent than the H plus and H2 couple. Positive potential means weaker reducing agent than the H plus and H2 couple. We saw, for example, copper and zinc. I hope you remember that, right? Copper, in that reaction, copper, you must see here, okay, in this right electrode, you can able to see copper, right? So what is happening here in the right electrode? Copper aqueous, it accepts 2 electron and becomes copper solid. Okay, so this you have to understand. Very important. Okay, it has positive electrode potential. So that's what we have discussed in this particular area. So this shows that, okay, so which is stronger? The redox couple is stronger if it is negative electrode couple, stronger than the H plus and H2 couple. Okay, so you know this, right? That means, H plus means it releases one electron, it loses one electron, and that electron is accepted by the uh, gas, and then it will be recorded as half of H2 gas. Okay, everything we saw. So similarly, this negative positive potential, it shows up. This redox couple is a weaker reducing agent than the H plus and H2 couple. Clear? Okay. So this is what you are going to write for Daniel cell. Concentrate copper 2 plus and zinc 2 plus. Okay. So for cathode, right side, so copper 2 plus copper, like this. We can able to write like this, right? Electrode of Mn 2 plus Mn, like this we can write Mn solid. Okay. Then it is the electrode potential minus RT by 2F into ln of 1 by copper 2 plus of aqueous. Okay. This achieved from, this equation is achieved from the above solution. Like, you must know how to write the reduction half reaction, oxidation half reaction, okay? Everything you must know how to write, okay? Right side is maximum reduction, left side is oxidation. We always use the reduction as the reference reaction, everything we saw. Okay. Okay, so it's not given here, but this was given to you from the chemical equilibrium reaction. So you have studied basically on grade 11 about the chemical equilibrium reaction. Okay, so it is RT by 2F into ln of 1 by copper 2 plus aqueous. Okay, same way for anode it is zinc 2 plus zinc means this will be standard electrode potential minus RT by 2F ln of 1 by, this is concentration, all these box, it represents the concentration of zinc 2 plus aqueous. What is the cell potential? You have to subtract both the things. So that is cell potential, both cathode and anode. Okay. Then, so what is the cell potential it represents? Here, this minus this. Okay. So you are writing the whole reaction minus this reaction. Okay. Then you can take up the first term and the third term separately and the second and fourth term separately. And then you can use the ln equation. So ln A minus ln B will be ln A by B. So ln A by ln B. So this is ln A, this is ln B means zinc 2 plus comes up numerator, copper 2 plus comes to the denominator like this. I mean concentration. I hope it is clear for your students. If you're not clear, then I'll write it again. Okay. See this one. E right minus E left. That's what given here. So this is E right minus E left. So you are writing these two and then taking the first and third term separately, and then second and fourth term will be there. If you take minus outside, then this is minus, okay, and then negative of this. So it will be already positive. Okay, if you take negative outside, then it becomes positive and then it becomes negative. So take down like this. And then RT by 2F is constant term. And then ln of A means 1 by copper 2 plus aqueous concentration by B is zinc 2 plus aqueous concentration. So it comes to the denominator, comes to the numerator. Got it? So this is what it can represent. It can be seen that the E cell depends on the concentration of both copper 2 plus and zinc 2 plus ions. It increases with increase on the concentration of copper 2 plus ions, decreases in the concentration of zinc 2 plus ions. Okay. So, and by converting the natural logarithm to the base 10 and substituting the values of R, F, and T is equal to 298 Kelvin, it reduces further to this. I'll explain you how to do everything. So R, T value and 2F, it is given. And then ln will be converted into log by taking 2.303 log to the base 10. Okay, then as usual, zinc 2 plus and copper 2 plus ions concentration. Okay, this R value, T value, and F value, I will explain you about that so it is easy for you to understand. Okay, then this is where I will show you now how to calculate. One second. So let us calculate now. What is the R value and everything we'll see. Okay. The R value is, can you all take down what is the R value means? R is 8.314 joule per mole per Kelvin. This is ideal gas constant, okay? This chapter is deleted for your grade 11, so you might not aware of this gaseous state. It is ideal gas constant. For the CBSE students, I'm telling. Okay. Then T is standard temperature. So here it is given 298 Kelvin. Okay. So it is basically 298 Kelvin means 298.15 Kelvin, or it will be 25 degrees Celsius. Okay, because 0 degree Celsius is equal to 273.15 Kelvin. This is the exact value. Okay, then F is nothing but Faraday's constant. This is 96,485. Okay, coulomb per mole. 96,485 coulomb per mole. It is Faraday's constant. Faraday's constant. Okay. So how many number of electrons are transferred? Number of moles of electrons transferred. So Cu2 plus and zinc 2 plus means N is equal to 2. That is the number of moles. Can you all write number of moles of electrons transferred? Number of moles of electrons transferred. This is N is equal to 2. If you calculate RT by 2F, that is equal to, you have to substitute everything, right? 8.314 into 298.15. divided by 2 times 96485. If I'm using calculator, it shows up